we've talked about calculating forces and electric fields of small charges, electrons, protons, spheres of charge. Now we want to think about getting the electric field of something larger, something macroscopic, like my Teflon rod. Right? So we know if we charge this Teflon rod up, it's going to be covered in charge, it's going to make an electric field. So let's think about now mathematically how to calculate the E field of and let's give it a fancy name instead of Teflon rod, a macroscopic charge distribution. So just like we introduced charge, thinking about microcharge, electrons and protons, macrocharge, large charge things, now let's think about the electric field that way. It gets a little bit complicated, so let's think about it for real. Let's think about my Teflon rod. Let's draw it on the board really large, okay? So there is Teflon rod. And let's think about what happens when we charge it up. We remember we rub it with the fur, and this is very electronegative because it has fluorine on it, so it ends up charged negative. So what that really means at the microscopic scale is that the negative charge on the surface, if we draw it like that, is really, if we were to zoom in to the microscopic scale, really just a little electrons on the surface sitting there. It's some density. Those that have been put on by the rubbing. If we were going to try to calculate the electric field of those electrons, it'd be really hard. We have the formula. We could say, imagine some point P over here, and we just apply Coulomb's law, essentially, to get the electric field of this electron, and then of this electron, and of this electron, and this electron. But the problem is, there are millions and millions and millions of electrons on the surface. So you would have to write an equation with millions and millions and millions and millions of terms. So we don't like to do that. Physicists are lazy. We would much rather find another way to do it than to have an equation with that many terms. So this is the reality over here. I want to stress that we are breaking with reality. The reality is millions of electrons. Okay? What we do in physics to avoid dealing with all those electrons is we make a model. Okay? In physics, when we say a model, that almost certainly means it's not exactly correct. It's something we do to make it easier mathematically. So this model, if you look at it microscopically, is this. The surface is negatively charged, which we might draw like that, but if you zoom in, you assume that the surface is just got a smooth charge on it. You could think of it as a fluid of charge. It's just some layer of charge such that if you zoom in, you still just see smooth charge. If you zoom in more, you still see smooth charge. If you zoom into the scale of an electron, you still see smooth charge. If you zoom into a millionth of the size of an electron, smooth. So the negative charge is smooth all the way down to the smallest scale that you could have, infinitely small scale. So the model is that we have smooth charge. And here you might characterize it with some number of electrons per meter. Here we characterize it with lambda, and lambda is the charge density, or in this case, the charge per unit length, which would be in coulombs per meter, charge per unit length. So we're going to use this model, and we're going to then calculate the electric field of a continuum, of a macroscopic charge distribution. Right? So I can see, oh, we have a question, so let's see what the question is. And let's see, Squareheart asks, will the charges really be evenly spaced? So that's a good question. Will the charges be evenly spaced? And the answer is probably not. Okay? So when I rub the rod with the fur, I get patches of charges here and there. I don't necessarily get them perfectly evenly spaced, which would be perfectly described by this model. And it's true, models are never perfect. Okay? When we use a model, we're making an approximation just to make the problem solvable. But it is highly unlikely that the electrons are perfectly smooth. Really, the question is, on the scale that we're going to calculate, if it's, say, tens of centimeters, is the charge smooth on that scale? And if it is, then it's a good model. If it has patches every tenth of a millimeter or so, they're charged or uncharged, it doesn't matter. If it has patches every 5 centimeters, then it does matter. So you always have to think about your model and decide if it's really good enough. So in this case, we're going to assume it's good enough because we're just doing freshman physics homework.